Hi, my name is Sherwin, and today I'll be covering fractals and Menger sponges. So, for context, the fractals are basically just detailed patterns with repetitions at every single level and scale. So, as you can see in the bottom right, or sorry, bottom left, there's these triangles that can be like the same triangular pattern can be applied every single level, and so like this pattern is essentially applied at any sort of level or any sort of scale, which makes it just infinitely applied. On the right, you can see an example of it being applied in nature with copper crystals, and so like you see like the that leafy pattern being applied as you get closer and closer into the actual copper crystal. And so for context with Menger sponges, they're basically a 3D fractal, three-dimensional fractal that was founded by Carl Menger, a mathematician. And they're and in order to like build a sponge, which I'll have a graphic later, is you essentially start with a full solid cube with six faces, and you'd essentially divide them into 27 smaller subcube sections, and you'd remove the central cube piece and the central cubes of each face, and you'd repeat this process infinitely so it brings out like a very interesting pattern. So for context, you can see here for layer one, it's just a regular cube. There's nothing going on with it. But for layer two, what you notice is that like the cube cutouts being shaped for 27 different times. And and this would be layer three. Now for somewhere in between, you want to look into layer two, which has just one single cube cutout. Layer four is one of the more expansive cubes with a full pattern being applied to at the fourth layer. So there's subcubes of subcubes of subcubes basically, and so it brings a very interesting pattern. And it's a reflection of a very common fractal. And so, in order to understand self-similarity with these Menger sponges, it's basically where a structure appears at various scales, so that basically if it can be applied at every single scale or very similar. Typically, in nature, it's tries to be similar, but it's not always identical. But for mathematical patterns and things like the Menger sponges, they're pretty much the exact same, regardless of which level it is. And it's useful to apply to natural scenes to make it more to make any scene more natural, or it's also helpful to simplify the explanation of complex systems and data. And so, as you can see here, this is what a level four Menger cube looks like, and you're basically looking at all of these different subsections of one, two, three, four, five, six, seven of these cube cutouts around a central cube. And that's the exact same thing that's happening for the larger cube, and that process gets repeated so on and so forth. And so that's essentially like the self-similarity factor of the actual pattern that you're applying to this entire cube. So when you're looking at a fractal's dimensions, it kind of represents the object's complexity. And it kind of like also helps visualize how these patterns get more complicated, deeper layers. And these fractal dimensions cannot just be described the integers. So like one dimensional would be a line, two dimensional would be a shape, and three dimensionals would be um, like an object like a cube or a prism or something of that nature. But fractals are a little bit more complicated, and so because that they have non-integer dimensions that you have to calculate. This is an image of a coastal fractal, well, a coastal fractal pattern where the pattern of a where as you increase in scale, the patterns of the coastlines keep expanding, but the pattern remains relatively the same. But as you get larger and larger in scale, you'll realize that there is like a coastline pattern that's applied regardless of which scale that you're at. And so whenever we're calculating a Menger sponge's fractal dimensions, what you're going to notice is that the dimension is calculated by log of n divided by log of s. So the log of n is the number of self-similar pieces, and s is essentially the scaling factor. For Menger sponge, the number of self-similar pieces is 20, and the scaling factor would be 3, and so your total dimension would be 2.7. So an image of this is like basically the cross section, and it makes sense because this dimension isn't essentially two-dimensional, but it's not three-dimensional either because of all the cutouts and all that nature. It's not a solid three-dimensional figure, but it's also not a solid two-dimensional figure. It's gonna be right in between, but leaning towards a three-dimensional figure more than a two-dimensional figure. So whenever we're looking at fractals in nature, we find that coastlines with irregular or self-similar patterns, like the picture I showed earlier, can be applied to differing scales. No matter like which specific scale it is, like there will be some sort of coastline pattern that can simplify understanding how coastlines are made. On the bottom right, there's an image with mountain ranges, and you can see that ruggedness is kind of repetitive regardless of how abstract you look at the picture of the mountains. On the left, you see the Romanesco broccoli with also like strong self-similarity in logarithmic spirals. And so that pattern shows so these patterns show how fractals are just made in nature, and they're very interesting to admire. In terms of applying fractals, it's common to use it in computer graphics, particularly creating like landscapes particularly for creating like realistic landscapes. So if we're trying to do something like that's mimicking nature, like for example, like a coastline or a mountain range, applying these fractals can be very helpful to create these realistic landscapes that are not always hard-coded. And for art, as you can see on the bottom right image, you can create visually stunning images and create complicated drawings that can be applied regardless of how close you are to the actual image. And for DNA, it can also be used to analyze protein structures, as in the bottom left. So you can see how there's like a common pattern regardless of the size of protein structures, which can be helpful for analyzing which can be helpful for understanding protein, but also looking into medicines as well. Another thing for fractals is understanding how chaos theory is related to fractals. For context, chaos theory is essentially a study of how initial differences can lead to much larger differences eventually. So on the left, you see the Mandelbrot set, which is a mathematical application, and see how like there's a overall overarching pattern of the circle and the other shape, and how that's applied regardless of which level that you're in. On the right, we're seeing an example of the Menger sponge where you might have a small difference of a small cube cutout for one of the smaller layers, but as you get more advanced, you'll apply that difference to other subcubes, and you get a much different shape compared to just a basic cube. In terms of future of fractals, it can be applied into like quantum physics and nanotechnology. It can also be used to explore high-dimensional fractals. Uh, and there's also like fractal-inspired AI models to improve feature extraction for models to understand certain patterns, and it's going to help with efficiency of deep learning. It's also helpful for energy efficiency for general systems because there's going to be a repeated pattern throughout, and that's very helpful for saving time and energy to be more efficient. All right, and that'll be all. Thank you so much.